Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This is the sixth and final video in a series on indeterminate forms and L'Hopital's rule for differential calculus. It is assumed that you know what indeterminate forms are. It is assumed that you know L'Hopital's rule. It's assumed that you've watched my videos on evaluating limits of indeterminate forms 0 over 0, infinity over infinity, infinity minus infinity, infinity times 0. Now we're going to deal with powers. So forms 0 to the 0th, 1 to the infinite, and infinity to the 0th. We only have two examples, honestly, so we're only going to capture two of those situations, but they all are treated the same way. So let's start with this one. Evaluate this limit as x goes to infinity of 1 plus x to the 1 over x power. This limit right here is a very, very special limit. And if you don't know it, it is a definition we introduced a long time ago for E. This is kind of a proof of E in a way. So let's see how this is done. If you were asked to evaluate this, and let's suppose you didn't remember that this is actually E to the first, how would you do it? Well, as x goes to infinity, you can see 1 plus x goes to infinity, but 1 over x goes to the 0th. So this is the infinity to the 0th situation, which is, what is it, the third form there? Doesn't really matter, they're all treated the same. How do you do this? Well, we're going to use a property of algebra. In algebra, I don't know if you remember, but b to the x, or I'll say b to the p for b to the power, is the same thing as e to the natural log of b to the p power. It's the same exact thing. And by the way, that means that we could take that power out of that natural logarithm. So that's e to the power times the natural log of b. This works as long as the base is positive, because you're taking the natural log of it. So that is a big heads up there, but that's okay. Our base is positive here, so we could totally do this. So this is the rule that you're going to use with all of them. Every instructor, I shouldn't say every, but instructors teach this differently from each other. This is the way I'm going to teach it here. So I'm going to say that this is the same thing as the limit as x is wandering off to infinity of e to the natural log of that 1 plus x to the 1 over x power. In other words, I am going to leave the e and the natural logarithm in the problem the entire time. The reason why I like to do that is because if you don't, I've seen students just forget that the e is there. So it's very important to just follow what I'm doing here. Follow my advice. This is equal to, well, since that base is constant, I will leave the base downstairs and I'll move the limit into the exponent. Again, the base does not have an x in it, so I can move that limit into the exponent. And the natural log allows me to pull this power out in front of it, so I have the limit as x goes to infinity of 1 over x times the natural log of 1 plus x. Again, all I did was rope up that exponent and pull it in front of the natural log. Now, if you look at this limit, I'm not looking at the base, I'm only looking at the limit itself. Notice that this tends to 0 and this tends to infinity. That's a 0 times infinity situation, but we know how to deal with that. Write it as a fraction instead. That's e to the limit as x goes to infinity of the natural log of 1 plus x over x. And now that is infinity, something approaching infinity, over something approaching infinity. That limit is ready for L'Hopital's rule. So I will say this is equal to, via L'Hopital's rule, e raised to the limit as x is running off to infinity. The derivative of the natural log of 1 over x is 1 over 1 plus x. I meant to say the derivative of the natural log of 1 plus x is 1 over 1 plus x. And then the derivative of that denominator is just 1. Now, of course, that's just 1 over 1 plus x. So I can just simplify it like that. As x goes to infinity, this fraction tends to 0. And so this is e to the 0th, which is 1. And there you go. That's how it's done. And by the way, I don't know if I said it earlier, but I might have misspoke. That is e to the 0th, not e. But it's a form of e. That's what's important. So there we go. We got that done. Now let's see how challenging these can be. That's probably pretty typical of these styles of problems. Just trade them out for e to the natural log of that limit. But now we're asked to evaluate something like this. The limit as x goes to infinity of the quantity 1 plus 3 over x plus 5 over x squared raised to the x. Now, as x goes to infinity, I hope you would agree that this entire base here will approach 1. And this exponent approaches infinity, obviously. So this is a 1 to the infinite power situation. Now, a lot of people will say, but 1 to any power is 1. I'm not telling you that that base is 1. I'm saying it's approaching 1. So therefore, you cannot say that this will turn into 1. And in fact, I don't think it does. So we need to manipulate this to be of the form infinity over infinity or 0 over 0. The way we're going to do that is the same way we did the previous problem. We're going to look at the limit as x goes to infinity, and let me write that in here, of e raised to the natural log of that function, 1 plus 3 over x plus 5 over x squared raised to the x power. Of course, that x, we can grab that guy and pull it in front of this logarithm. Also, because e is a constant, I can move the limit into the exponent. So that's what I'm going to do in my next step. This is just going to equal e raised to the limit as x wanders off to infinity of, well, we removed the exponent into the front of the logarithm. And so we have this situation right here. 5 over x squared. As x goes to infinity, now I'm just focusing in on the limit itself. As x goes to infinity, you'll get the following. I'm going to use green. This factor tends to infinity. And this whole piece right here tends to the natural log of 1, which is 0. So we have a 0 times infinity situation. Remember my advice. Leave the object in the numerator that will eventually change forms. The one of these two objects that will change forms, actually they both will change forms. If you left the x in the numerator, its derivative would be a constant. If you leave the natural log in the numerator, its derivative would be the argument, right? 1 over its argument. So it really is dependent upon how you want to do it. I would probably put the most complicated piece in the numerator of those two choices. So that's what I'm going to do. I'm going to write this as e raised to the limit as x tends to infinity. I'll leave the natural log in the numerator. 1 plus 3 over x plus 5 over x squared. And I'll move that x to the first into the denominator by calling it x to the negative first. If you look at that, it is the same statement as the one above. So these are equivalent statements. But now, as x goes to infinity, you get the following. The natural log of 1 in the numerator, which is 0. And this is 1 over x. As x goes to infinity, that will approach 0 as well. So now we can use L'Hopital's. I need to remove that green ink so I can see what I'm doing. So using L'Hopital's here, equals via L'Hopital's rule, we have e to the limit as x goes to infinity. The derivative of a natural log is 1 over its argument. So this is going to be a bit of a mess. It's 1 over 1 plus 3 over x plus 5 over x squared. But then you have to take the derivative of this argument of the natural log. Derivative of 1 is 0. The derivative of 3 over x is going to be a negative 3 over x squared. The derivative of that 5 over x squared is a negative 10 over x cubed. That's just those derivatives. You can't avoid that. In the denominator, the derivative of x to the negative first is negative x to the negative second. But I'm going to write that actually as negative x or negative 1 over x squared. I just think it's a better choice. Now, some algebra, right? And here's how I'm going to do my algebra, because I just think that it's better to do it this way. I am going to start by moving this x squared. Let's see, what's the best way to say this? Probably the best way to say it is just to say, I don't like having this negative 1 over x squared downstairs. So what I'm going to do is multiply this entire numerator and this entire denominator by a negative x squared. I'll start there. I could do it in pieces, right? So doing that is my first step, and it just allows me to not have such a compound fraction. I'll have e to the limit as x goes to infinity. This negative x squared, it would park into the numerator, right? But actually, this is what's in the numerator. So I'm going to distribute that negative x squared to each of these terms instead. So I'll just do that. There's no reason for me to park it, because that parenthesis right here is going to be in the numerator of this fraction upstairs. So I'm just going to park a negative x squared into each of those pieces upstairs. That'll give me a positive 3 plus 10 over x, and that's being divided by 1 plus 3 over x plus 5 over x squared. Now I'm going to go ahead and actually be done. Because if you look at it the way I've written it, as x goes to infinity, this tends to 0, this tends to 0, and this tends to 0. That was just by chance. And so we get 3. But not just 3, it is e to the third. There you go. That is the actual value of that limit. And that rounds out all of L'Hopital's rule. Remember, when you're evaluating limits of the form 0 to the 0th, 1 to the infinite, or infinity to the 0th, you're going to trade out those functions for e to the natural log of those functions. And that will allow you to unlock those exponents and move those exponents out in front. And then you would be able to manipulate them so you can use L'Hopital's rule.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.